Hello, my name is Nevada Simpson, and today I'll be talking about our conference publication, Sleep Regularity Modulates the Effect of Sleep Duration on Long-Term Memory Function in Healthy Undergraduates. First thing I want to talk about is why we decided to do this study. So the impacts of sleep on memory have been studied for a long time, and a lot of that research has gone into the impacts of getting fewer hours of sleep, sleep restriction, or complete deprivation in experimental contexts. This has often been defined relatively modest effect sizes of maybe 0.2 to 0.4 standard deviations of change with a night of complete deprivation before the test. This may be partially because there's a lot of noise in the way most people measure memory. Most of it is sort of learn a set of things 8 hours ago, test on it 8 hours later. And that might be prone to just a decent amount of error. There's also just been a long-standing focus on sleep duration instead of necessarily looking at sleep quality, which we know is very important, especially from looking at disorders like sleep apnea. Part of the reason sleep apnea is so harmful is not just because you get a less duration of sleep when you're waking up in the middle of the night, but you also are being prevented from getting to those deep states of sleep, like deep non-REM as well as REM sleep. And those seem to have a particularly important impact on the body and the brain. Another important aspect of sleep quality that maybe is even more understudied than like sleep phases is sleep regularity. And it's essentially going to bed at the same time between days and waking up at the same time between days. And we know this now has really large health impacts. In fact, one study I like to look at here is Windrit et al., which found that sleep regularity better predicted all-cause mortality than sleep duration. And here to simply explain their results, on the x-axis you have the years since their recording, on the y-axis you have proportion surviving, and then you have quintiles for sleep regularity on the left and quintiles for sleep duration on the right. And the regularity has a very clear directional effect of the more regular you are, the better your odds of all-cause or the better your odds of survival over the study period, the better your all-cause mortality odds are. Despite this, we really haven't studied the effects of sleep regularity with memory very much. So how did we decide to go about this? Well, we wanted to have a good working model of memory so that we could measure it well, and we decided to use the ACT-R memory model. So the ACT-R memory model basically posits that when you learn information, it creates a neural trace of that information, and that this neural trace, if there are multiple traces, becomes the activation of the memory, so how strong it is in your mind. And the activation can basically be also considered the odds of recall of that memory. Each of these neural traces is subject to a decay over time by this characteristic decay rate D. The characteristic decay rate can be further subdivided into this e to the a term, which demonstrates that information that you know already very well will decay rather quickly when you relearn it. So if I say my name is Nevada again, that information does not do a whole lot for me in terms of memory. That trace will decay very quickly. It's not like I know my name much better after having said that, right? But for you, and you've only heard it now twice, that will make a very big difference because your activation was not already very high. And then there is this added speed of forgetting component, which is sort of this cross-subject rate of forgetting that can be considered someone's overall memory quality. Because this speed of forgetting, when it is high, your memory is bad, when it is low, your memory is good, we invert that to communicate it better with participants and turn it into a sigma score with our test. Here is the ACT-R memory, or the ACT-R model of memory in action. On the x-axis here we have time, and on the y-axis is activation. There are 3 neural traces in this example, and you can see over time they add up to form the overall memory activation. And on the right here we have a couple sample sigma scores. Remember, higher sigma score meant better memory, lower sigma score meant worse memory. And the x-axis is the log time scale, and the y-axis is a recall probability for this information. And here's how some sample sigma scores give you different probabilities of recalling that information, or the same probability of recalling that information over different timescales. For some context, so these numbers are meaningful, 100 is considered to be the population average, roughly. Below 50 would be considered very low, possibly pathologic, and a very strong undergraduate, as we'll see, might have like a 120 to 140. The ACT-R model also makes predictions about the response time, which depends on the activation of the memory. So it makes sense that if you have very high activation for a memory, your A term is very high, your response time will be substantially lower. And so the response time thing has two components. It has T0, the simple processing time of the information, is essentially just how long it takes for you to respond to a basic request, right? It's just information processing time. And then a activation term A, which determines how strong that memory is in your brain at the time, and a decision boundary F, which determines essentially how much evidence you need to be willing to give the answer, how long you're willing to wait to process that information and like try and pull that memory out. And so here's what our test actually looks like, our sigma test. It is a paired associations test where you're given, in this case, an image of a jellyfish in the name, and then delayed a certain amount of time, depending on the test's estimation of your sigma score. You'll then prompted to answer what the correct name for this jellyfish is. If you recall it correctly, it will adjust up your sigma score and delay longer the next time. If you answer incorrectly, it will adjust down your sigma score and delay for a reduced amount of time on the next time you're given the information. And here are some sample sigma scores and sort of how that contextualizes in the range of adulthood. So when you're young, you probably have like around a 110 is sort of the average. When you're older, closer to 90, 80, even lower. And as we'll learn, our UW undergraduates are pretty exceptional, and they're sort of up in that 120 range. And speaking of our undergraduates, they were all recruited from a UW bio course. They're all, as such, going to be around the same age, mostly juniors and seniors. And as part of this course, we had their sleep tracked for 3 weeks using accelerometers. Each of these 3 weeks, they performed a memory test in class at 9:30 a.m., bright and early. And they all had the same test order, first a test on pasta, then birds and jellyfish. To measure the sleep, we used AX3 watches. The sleep recordings here gave us a pretty good idea of when they were asleep versus awake based on their movements. And we use this to measure the onset and offset time of sleep, which is sleep onset when you fall asleep, offset when you wake up, which you can use to calculate the total duration, as well as the sleep regularity index, which the sleep regularity index basically compares the previous day of sleep to and wakefulness, so the previous day and your sleep states during that day to the current day and your sleep states during that day, so whether you're asleep or awake. And when those match up, you would get a higher score. When those do not match up, you get a lower score. And it is set up such that a 100 sleep regularity index means they're perfectly in phase. A 0 sleep regularity index meant they were perfectly random. And a negative 100 sleep regularity index means they're perfectly out of phase. So if you were asleep on Wednesday, you would be awake on Thursday. If you were awake on Wednesday, you'd be asleep on Thursday, is how a negative 100 would actually look. And then we compared all that previous night data with our sigma scores, our memory outcome data. And here are our results. Here is really our big takeaway result from this, and that is that the sleep duration did positively associate with memory, but that regularity actually had a compensatory effect. So here on the x-axis of this figure, we have the centered sleep duration. This is a measure of sleep relative to that person's average, to that individual person's average. So if someone normally gets 8 hours and they're negative 2.5 on the x-axis, they were getting 5.5 hours. And then on the left is our sigma scores. Once again, our undergrads are exceptionally around the 120 average range. And here what we can see is that there are 3 lines, with the solid line representing our high sleep regularity group, the large dotted line being our mean group, and the small dotted line being our low sleep regularity group. And the clear effect here is that the low sleep regularity group is benefiting the most from additional sleep, whereas the high sleep regularity group doesn't seem to be benefiting much from the additional sleep. Another way of viewing this is that the sleep duration is important, but if you have low sleep duration, it might be that good sleep regularity is able to compensate for that effect. What sleep regularity did have an effect on as the main effect was the decision boundary F. So here on the x-axis we have the sleep regularity index. Once again, this is the day before they take the test. And on the y-axis we have the F parameter, which was extracted from the model. And the F parameter really represents, again, how long they were willing to wait before making a decision on a test answer. Or, if you were thinking in terms of a linear ballistic accumulator or something like that, it would be a decision boundary. And in this case, we also have different groups for the, a substantial effect of the interaction of sleep duration with sleep regularity. But this time, this interaction is positive, such that when you got sleep regularity that was high and sleep duration that was high, these seem to have an additive effect. They benefited each other instead of the compensatory effect we had previously seen. And this is interesting. It's almost like a way of saying people with high sleep regularity and high sleep duration are being more careful with the exam is one potential way to view this. And so what do these results mean, and what would you like to do in the future? Well, some basic conclusions. Reduced duration of sleep means you forget quicker. This is unsurprising. This is in line with previous evidence and is a good sanity check. What is interesting, though, is that high sleep regularity could compensate for some of the negative effects that you might have gotten from low sleep duration, which is maybe a meaningful takeaway in terms of if you're forced to get poor sleep duration for some reason, maybe try and have that sleep happen at the same time every day. Or another way of viewing it is if your sleep's going to be irregular because you're like a shift worker, maybe try and get some extra sleep. In addition, we found that sleep regularity positively correlated with the decision threshold. This was our F in our model. And this effect seemed to be complementary with sleep duration as opposed to our other finding. As for some limitations, we had a relatively small sample size, 29 people and 3 tests per person. So if there is a direct effect of sleep regularity on our memory outcomes, it might just be that we were underpowered to find it. We did find non-significant effects in that direction, so I wouldn't be surprised if more data found that to be the case. We also only studied young adults who may be just particularly resilient to the effects of a single night of bad sleep. If we're looking at older individuals, it might be that low sleep regularity the night before would crush them in the memory test the next day. It's just, we don't know. We also had a consistent testing time, but that consistent testing time was early and may have artificially introduced some effect on night owls. It could be that the night owls, had they taken the test later in the day, would actually be more awake, independent of how much sleep they got that night, because they're just groggy in the morning. And then we also had a very high lesson accuracy, because while this test does adapt, when someone's got a 160 sigma score, it takes a long time to adapt because its assumption for the baseline is so much lower than that person would be. And so in that case, the test might have been too easy for them to meaningfully be challenged. And I want to give a thank you to my collaborators on this. They've been wonderful. Anais from the Precision Cognition Labs, especially with help writing the paper. Andrea from the Cognitive and Cortical Dynamics Lab. And then Horacio and Guadalupe from the De La Iglesia Lab for all their help collecting the data. And thank you for watching.